Good morning, good morning, good morning, and welcome. Today I'm going to go through a 2024 paper 1. 2024 paper 1. So I'm only going to concentrate on climate and weather from 1.1 to 1.5. Then after that, if time permits as well, I'll look at section B, that is MAPWEC, but only for this lesson I'm going to look at section A, which is climate and weather. I'll read, try to give the answer as well, and try to explain so that I make some of the concept as clear as possible. So section A, refer to the sketches in A and B. Various options are provided as possible answers to the following question based on the influence of anticyclones in South Africa. Choose the answer and write only the letter A to D. Write only the letter A to D. So I think before I start with the question, we need to have a better understanding of what an anticyclone is, okay? And also the anticyclones in South Africa, I'll say, okay, so that at least you have a better understanding of what we are talking about. So I'll just try to illustrate, okay, the anticyclones, which is the high pressure system. We're basically talking about the high pressure system and also their location. So here what we have got the South Atlantic High. Here we have got the South Indian High. Then there we have got the Kalahari High. So that is the first thing that you have to know, the positioning of the anticyclones in South Africa. The influence, of course, we talk about that, but you have got the South Atlantic High here. You see, obviously, and we have got our, on the west coast, we have got the South Atlantic High. Then here we have got the South Indian High. Then we have got the Kalahari High. That's the first thing that you need to understand in terms of their positioning before we attempt to answer any questions. So you've got the South Atlantic High, you've got your South Indian High, you've got your Kalahari High. So these three high pressure systems, they change their position depending on the position of the ITCZ, which is our intertropical convergence zone. I'm going to talk about what happens in summer and also what happens in winter. So what happens in winter is during winter, the Kalahari that is in the interior is very active. There's too much subsidence that is taking place in the interior. So as a result of too much subsidence, which means the wind that is blowing towards the interior cannot go above the escarpment, we have got clear, calm conditions within the interior because the Kalahari High is very active. It's not allowing the wind that is blowing from both the two high pressure systems to go towards or above the escarpment, because when it goes above the escarpment, if it's warm, what happens? It cools, it condenses, clouds form, then we have got rainfall. So in winter, the Kalahari is very active, which means there's too much subsidence that is taking place. That is number one. Number two, our ITCZ has changed its position, which means it's on top of the equator. It's in the northern hemisphere, it's on top of the equator. So when our ITCZ has changed the position, it means now our South Atlantic High, it moves further north. Our South Indian High, it also moves what? Further north. Our ITCZ, now we are saying now our ITCZ is on top of the equator or is in the northern hemisphere. So now here in the interior, that's where we have got our Kalahari, which is the other anticyclone. It is very active. There's too much subsidence. Okay, there's too much subsidence that is taking place, which means the wind that is blowing towards the interior cannot go above the escarpment. Because when it goes the escarpment, of course, I'll talk about what happens in summer. So this is basically explaining the situation that is happening in winter. So the Kalahari is very active. Our South Atlantic High has shifted its position. It has moved further north. Our South Indian High has also shifted its position. It has moved further north. Then our Kalahari is very active. Our ITCZ has also moved in the northern hemisphere, that is, it has moved on top of the equator. So it means when you want to see now whether it's winter or summer, so it means when it's winter, A describes winter. Why? Because there's an H which is high pressure. There's an H which is high pressure, so it describes winter. That is A. diagram A. Then here, that is your coastal low. Remember, we have got the berg winds that are associated with so that are usually occurs in winter. So we've got the high pressure system here, Kalahari. We have got the South Atlantic high here. South Atlantic high, it has moved further out north. You can see here we've got South Indian high, it has also moved further north. Then we've got our low pressure here, which is the coastal low that we find at the coast. Okay, this is a situation that explains what happens in winter. Of course, sometimes you can have on a synoptic map, you can weather map, you can have the date that shows you that is winter. You can also have the look at the position of the cold front, which is supposed to be close to Cape Town. I think it also tells you that it's winter. But if you look at B now, this is now a typical summer because of intense heating in the interior. We have got a low pressure here, and you can check the position of our South Atlantic high. It has moved further south. Why? Because of the change of the ITCZ. ITCZ, intertropical convergence zone, now is below the equator, which means that's why we have got the thermal low, we have got the intense low pressure that is within the interior. Then you can also see with the shifting of our high pressure system, if you are to compare the two, you can see here they moved further north. Here they moved further south because it's summer, which means there is low pressure. Of course, I'm not going to talk about the line of thunderstorms. I'm not going to talk about the moisture front, but I just wanted you to have an understanding of the movement of the high pressure system. Here in winter, they move further north, and our Kalahari is more active in the interior, which means there's too much subsidence that is taking place. No wind that is blowing into the interior will be allowed to go above the invasion layer or above the escapement. When it goes above the escapement, that's when we have condensation, clouds form, then we have got rainfall. Okay, which is a typical summer condition. So here there's too much subsidence. We've got high pressure, we have got a coastal low pressure. Our high pressure, that is your South Atlantic high and South Indian high, they have shifted further north. Okay, in summer, you can see due to intense heating that is happening in the interior, we have got your two high pressure system, they've moved further down south. Our Kalahari is there, of course, but it's not as active as it is in winter. That's why we have got an L, which means a low pressure. So whenever you see, even in a synoptic weather map, when you see low pressure in the interior, that's summer. When you see high pressure, that's what? That's winter. Okay, let's go to the question line. The typical A shows which conditions are being shown there. You can see from the explanation that I was giving that this is a typical what? That's winter. Why? Because there is high pressure in the interior, which is our Kalahari high anticyclone is very active. You can also see with the position of our two high pressure system, that is your South Atlantic high and South Indian high. They have changed their position. They've moved further north. Okay, you can also see with the presence of the coastal low there. Okay, then the low pressure system in sketch B forms due to, obviously, remember I was talking about the intense heating that is happening in the interior. This is coming from the land. So your answer there will be B. Then is the concept used to describe the elongation of isobars with the with the South Atlantic anticyclone in sketch B. Of course, this one is ridging. When you talk about backing, we are talking about the low pressure, okay? So this one here is what is ridging to diverge. Remember what happens, especially in high pressure system, pressure belts, there is divergence, which means in the subtropical high, the other one is moving towards the subpolar, the other one is moving towards the ITCZ or equatorial low. That's where diverging is taking place. Convergence, moving towards each other. Look at what happens within the equatorial low. Basically, what I'm saying is, when you look at this diagram, I'll take you back like to global air circulation. This is 0, 30 degrees north. This is 30 degrees south. Okay, so when it's moving towards the equatorial low, remember this is high, this is low, this is high. Okay, this is low, this is high, this is low, this is high. So we've got the equatorial low pressure. This is subtropical high pressure. So it moves towards the equatorial low. That's what we mean when we talk about convergence. It's converging at this ITCZ or the doldrum, equatorial low. This is low, this is high pressure. If you can check also from this high pressure, it moves towards the subpolar. This is basically what I'm talking about. It's moving towards the subpolar. So if you look at the subtropical high here, there is divergence that is taking place. Obviously, it's the concept of pressure gradient from high to low. That's how our wind moves. It moves from high to low. So here there is divergence that is taking place from high to low, subpolar, low. Here from subtropical high toward the equatorial low, that is convergence that is taking place. Here that is divergence that is taking place, which means to diverge away from each other, converging, moving towards each other. Okay, so the answer there is region. The anticyclones in sketch A and B change their position seasonally because of, remember I was talking about the shifting of the ITCZ. Remember in A, we are simply saying that our ITCZ is shifted, is north of the equator. That's why our Kalahari is very active. Okay, that's why you can see also that our high pressure system, that the South Atlantic high and the South Indian high, have changed their position. They change their position, move further north. Okay, move further north. Why? Because our ITCZ has shifted, is north of the equator. In summer, you can see now our ITCZ now is moved further south, which is south of the equator. That's why you see our high pressure system, they also move further down south. So the answer there is shifting of the ITCZ, which is the intertropical convergence zone. Okay. Then number 1.1.5. The South Indian anticyclone sketch B is likely to feed more moisture over the east coast in comparison with the sketch A because of, that is 1.1.5. Okay. All right, we are talking about this. It's likely to feed more the south, meaning you can see, can you see the area that is covering, compare the area that is being covered by in winter or in summer. We're talking about the situation in summer. Likely to feed more moisture at the east coast comparison to sketch A. Okay, because, all right, it has got a larger fetch distance. You can see. Obviously, let me just try to introduce the concept of air mass. What is an air mass? A large body of air with similar characteristics in terms of temperature and moisture. So which means if it is covering a larger distance, it is a larger fetch in terms of distance. It means even where it's coming from, as it is going over, it is blowing over the warm oceans, which means what it's going to do is going to absorb more moisture. You understand? It's going to absorb more moisture. Remember, this is coming from a warm ocean. So as it passes through the surface, which means the characteristics in terms of moisture content, in terms of temperature, are also changed. You understand? So it becomes warm, more warm and moist, which helps to bring more rainfall into the interior, especially in summer. Obviously, I'm talking about your South Atlantic and South Indian high. Of course, they are separated in the interior by a moisture front. Of course, we may have more rainfall on the eastern side. So basically, that's what I'm trying to say, that it has a larger fetch distance. That is the answer there, which means the answer there is what? B. Number 1.1.6, the low pressure system in sketch A will move in A, low pressure system in A. All right. Low pressure system in A, 1.1.6, 1.1.6. Okay. Low pressure, this is the low pressure system. Okay. It will move in. The answer there is easterly. Remember, it moves along the coast, okay? Easterly, which means it's going towards the east. The east is on your right, okay? So it will move in an easterly direction, which is 1.1.6. Then back winds are most likely to develop in sketch A because of the presence of, what do we have? We have got the Kalahari high, we have got the coastal low. We have got the Kalahari high, we have got the coastal low. Let's check there. We have got the Kalahari high, 1.1.7, Kalahari high. Then we have got the coastal low, which is 1 and 2. Okay? All right. Which is the Kalahari high. Then we have got the coastal low. This is the Kalahari high in the interior. This is the coastal low at the coast. That's why I'm saying it moved towards the east. Okay? So moving along the coast. Okay? Then the invasion layer that forms over the escarpment in sketch B will favor the formation of 1.1.8. We have our answer there is 2, obviously rainfall and hail. That is 2 and 3, which gives us what? 2 and 4, sorry, which gives us C. Remember what happens here in sketch B. we have got the South Indian High, we have got the South Atlantic High, then we have got the low pressure in the interior. Obviously, during this time, this season, we have a moisture front. I'm going to draw the line that cuts across. We have a moisture front that separates the cold air from the South Atlantic High and the warm moist air from the South Indian High. A zone or a boundary that separates the cold air from the South Atlantic High and the warm moist air from the South Indian High. That's where we have got our moisture front. I'll just say MF. Obviously, this is warm and moist. So when they meet in the interior, separated by the moisture front, the cold air coming from the South Atlantic High, what does it do? It's dense, it's heavy, it uplifts the warm air from the South Indian High that is coming from the northeast. This is coming from the southwest. So it uplifts it, and as it is forced to rise, what happens? It cools. When it cools, condensation takes place. Then clouds form, especially cumulonimbus. It forms on the eastern side of our moisture front. This is where we have the thunderstorm, where I've written the T. This is where we have a line of thunderstorms. So we are likely to have rain and hail, which is a heavy rain in most cases. Why? Because now we have got the intense low pressure in the interior, and we have got a moisture front in the interior that separates the cold and dry air from the South Atlantic and the warm and moist air from the South Indian High. It's separated by the moisture front, which is a boundary or a zone that separates those two air masses. So as they meet in the interior, the cold, denser air uplifts. There's massive upliftment that takes place of the warm, moist air that comes from the South Indian High. And as it rises, clouds form, condensation takes place. Then we have got rainfall. We have got a line of thunderstorm on the eastern side of our moisture front. This is what happens. So the answer there, we are saying that there will be rainfall and hail, which is C. 1.2. Match the descriptions below with sketches, A and B. Write only A or B next to the question numbers 1.2.7. Answer book 1.2.8. Refer to the sketches A and B on valley climates below to answer the questions. Okay, when you talk about the valley climates, we are talking about the microclimates. Micro, we are looking at those small areas. Why are those areas having a climate that is different from the surrounding area? Like your valley, like your urban areas, why are they having a climate that is different from the surrounding rural areas? That's basically what we are talking about. That's basically what we talk about when we talk about what we call microclimates. Okay. So what we have here in the diagram, before we start doing anything, you remember the concept of anabatic and katabatic wind. Okay, so here during the day, obviously, that's where we have got warm air that is rising. That is your B. You have got your warm air that is rising. This happens during the day. This is your anabatic. This is your anabatic, okay, wind, okay? Then here, this is your katabatic. This is during the night. Remember, cold air, warm air, let me start with B, okay? Warm air is light. So what it does is it rises. And as it rises, this is replaced by the air that is slightly colder than it is. Okay, so this is warm air. Warm air rises because it is light. It rises, cools, condenses, okay? Then cold air is very heavy during the night. This is where we have got your katabatic during the night. Cold air is dense. So what it does is it sinks. It subsides. It sinks, it subsides. That's what cold air does because it's heavy. Okay, it doesn't rise. Okay, so that is your katabatic, that is your anabatic. Okay, 1.2.1 represents the anabatic wind, which means that is your B, which happens during the day. That is warm air that rises. Okay, cold air forces the warm air to rise, which forms an invasion layer. 1.2.2, that will be your A. Why? Because an invasion layer, it forms during the night, cold, calm, clear, nice. Because we are now saying now, as this cold air is descending, is subsiding, okay, what happens is the Warm air that is beneath here will be forced to rise. So when it rises, it means now it's going to be trapped by this cold air from the top and cold air at the bottom. That's how we're going to end up having an invasion layer. So this will happen in A. Okay. Occurs during the day due to insolation. Insolation is simply incoming solar radiation. Incoming solar radiation. So that will be your B. Number 1.2.3, incoming solar radiation. That will be your B. Frost forms on the valley floor when the temperature drops below 0 degrees Celsius, 1.2.4. Remember, this is during the night when cold air is descending, but the temperature is to be below 0 degrees Celsius. Okay, that's what we are saying. So that will be your A. That will be your A. That's when we have got frost pockets. Okay, that's when we have got frost pockets, or we have, that's when frost forms, because when temperatures goes below 0 degrees, obviously is during the night when temperature drops below 0 degrees Celsius. That's when we have got the frost pockets. Refer to sketch A and B on pollution domes below to answer the question 1.2.5 and 1.2.7. We have got an urban area during the day. There's more pollution. Obviously, you can see the pollution dome. That's the layer of pollution that is above an urban area. That's what a pollution dome is. Okay. So from the options that are given, 1.25, this is okay. This is also urban area. This is urban area. So the question reads 1.2.5. Represents pollution dome at night. This is the one that represents pollution dome at night, because obviously the concentration is too much during the day. You can see there small pollution that is taking place during the day. You can see this A. So 1.2.5 during the night. That here is what? Is B. Okay. Pollutants are dispersed. They are dispersed, especially during the day. That will give you your A. Then a denser concentration of pollutants over the urban area. Obviously, it is suggested that over the urban area, you have already said that represent pollution at night. This is B. So which means now our answer is what? Our answer is B. There is our answer there. Okay. Let's move on to the next one. Let's move on to the next one. Refer to the cross-section below of mid-latitudes. Refer to the cross-section below of mid-latitudes. Okay. In which direction does the mid-latitude move? So here I want to demonstrate something. Okay, I want to demonstrate something before I answer that question. Okay, when we talk about mid-latitudes, I'm going to explain using this. Okay, this is your 30 degrees north. This is your 60 degrees north. This is your 90 degrees. All right, 30 degrees south, 60 degrees south, 90 degrees south. So what you need to understand is you need to have an appreciation of the knowledge of global air circulation before you attempt to do this mid-latitude tropical cyclones. I think to make your life easier, the first thing is at 0 degrees, what we have got low pressure, which is our equatorial low, or the ITCZ. We have a low pressure. Then we have got high pressure at 30 degrees north and south, which is our subtropical high pressure. This is grade 11 knowledge, okay? Then at 60, we have got low pressure, 60 degrees north and 60 degrees south, which is our subpolar low pressure. Then at 90, we have got high pressure, which is our polar high. So you need to understand, you need to have this foundation so that at least it makes it easier for you to understand mid-latitude and even tropical cyclone. So this is a distribution of our world pressure belts. We have got a low pressure, which is our ITCZ, okay? We have got high pressure, subtropical high, both north and south of the equator, 30 degrees north and south. Then we have got subpolar low at 60 north and south. That we have got a subpolar low. So we have got low pressure, high pressure, low pressure, high pressure, our polar high. So the question now is talking about mid-latitude. So the mid-latitude is in the middle of the latitude. This is where we find them. That is from 30 degrees north and south. This is where we find them. Okay, before we move on to where we find them, okay, so here we have got what we call tropical easterlies. Okay, I'll say E, tropical easterlies, close to our ITCZ, close to our equatorial low. Then here we have got the westerlies. Here we have got the polar easterlies. We have got the westerlies. Then we have got the polar easterlies, PE. PE. Here we have got the tropical easterlies, we have got the tropical easterlies. So in order for you to know what drives the mid-latitude, in order for you to know in what direction does it move, you need to have an understanding of what happened in the global air circulation. So you've got your, within the tropics, okay, easterlies, okay. So when you talk about the tropical, of course, I don't want to mix things. Let me stick to the mid-latitudes, okay? Easterlies drives whatever is taking place here. Then here is where we have got our mid-latitudes, which means it's driven by the westerlies, and it moves from west to east. That's what it means, move from west to east, or it's driven by the westerlies, okay? So we have got two air masses. The one that is coming from the subtropical high is warm. The one that is coming from the polar high is what? Is cold, and is separated by a polar front that is at the subpolar low, okay? Let me go to the question now so that I don't confuse you. In which direction do mid-latitude cyclone move? So here now you can see even the direction is shown from west to east. It moves eastwards. This is the same thing that what I was talking about. It's driven by the westerlies. So it moves from west to east, okay? Or it moves eastwards, okay? That is the answer then. Give a reason for your question in 1.3.1 is driven by the westerlies, or okay, is from the west, okay? Driven by the westerlies. This is where we've got our westerlies. This is where we've got our tropical easterlies. So this is what drives the mid-latitudes. It's found between 30 degrees and 60 degrees south, okay? Then how does the front A give rise to the formation of cumulonimbus clouds? So the front A, what is it first? That's what we need to understand. Is a cold front. A front A is a what? Cold front. This is your warm front. So they are asking, how does it lead to the formation of cumulonimbus clouds? So what you need to understand is the cold front will undercut the warm air. Remember, behind the cold front, there is cold air. Ahead of the warm front, there is warm air, which is the warm sector. So the cold front will undercut the warm air, which means there's massive upliftment that takes place of the warm air, and there is also steeper pressure gradient behind the cold front, which will cause the upliftment of the warm air. Cooling and condensation occurs, result in the formation of cumulonimbus clouds. So there is massive upliftment that happens because there is cold air behind a cold front. Ahead of the cold front, there is warm air. So there's massive upliftment that takes place of the warm air, and it cools. As it cools, it condenses, then clouds of vertical extent like cumulonimbus clouds form, okay? This is what happens, okay? Cold front will undercut the warm air ahead of it. So there's cold front behind there's cold air behind the cold front. Ahead, there's warm air, okay? So what happens? The cold front, okay, the cold air behind the cold front will undercut the warm air, causing it to rise, condenses, then cumulonimbus clouds form. In a paragraph of approximately 8 lines, explain the strategies. Explain the strategies that can be put in place to manage the negative impact of the heavy rainfall associated with mid-latitude. Of course, mid-latitude is associated with what? Heavy rain. So we are now saying that there are negative impacts that are caused on the environment. What strategies can be put in place to make sure that we control, okay, those negative or manage those negative impacts? So the first thing that we can do, remember, the focus is on the natural environment. We can maintain natural vegetation. That's the first thing that we can do. We can maintain natural vegetation. Maintain natural vegetation. I'm doing 1.3.4. We can encourage afforestation. We can buffering of the area. That's one thing we can do. We can create effective drainage systems. The use of sandbags. We can use catch nets, also prone to rockfalls. Construction of dams or wells. We can construct artificial levees or barriers. Levees are just raised banks. Okay, we can conserve wetlands, marshes, and swamps. We can implement contour plowing, terracing of slopes, educate people about environmental conservation, awareness, or early warning systems. So all those things that I've just said, now you can choose only 4. Maintain natural vegetation, encourage afforestation. I'm just going to say that's the easy one that you won't forget. Educate people about environmental conservation, awareness, early warning system. So these are some of the things that you can actually implement to manage the negative environmental impact of heavy rainfall associated with the mid-latitudes. Obviously, we're talking about the effects that we have as a result of floods. That's basically what we're talking about. Okay, number 4. Refer to the infographic below based on tropical cyclone Filipo. Filipo. Okay, by just hearing this word Filipo, you know that your tropical cyclones, they are named alphabetically A, B, C, D, E, F, which means this is the 6th cyclone during that season. That's what should come to your mind. Okay, the tropical made landfall in Mozambique on 12 March after strengthening off the coast of southern Africa, bringing strong winds and heavy rain to Mozambique. Obviously, from these, you are now knowing that tropical cyclones are associated with the heavy rainfall and strong winds. So already, you know that it's associated with strong winds and heavy rainfall. On March 13, tropical storm Filipo moved back over the ocean and developed into the tropical cyclone. The movement of the tropical cyclone. Okay, so this is what we have. It shows this is the eye of the tropical cyclone. You can see in terms of its movement, you can track it, okay, from here, how it moves, 11, 12, 13 March up until it's here. You can see we're trying to track its movement. You can also check the information that is given here from 10 to the 14th month, the changes in terms of wind speed. You can see when it was destructive and when it was less destructive because of the speed, the wind speed. You can also see what is shown here. This is a stage in the development of tropical cyclone, which is the mature stage. You can see the eye. You can see also the left quadrant, which has got more windy, which has got more unfavorable weather conditions. 1.4.1 in northwestern. State one condition that could have led to the development of tropical cyclone Filipo. So what is needed here, boys and girls, is you should know the conditions that are necessary for the formation of our tropical cyclone. This is what they are asking indirectly. State one condition that could have led to the development of tropical cyclone Filipo. So already, if you know the conditions that favors the formation of our tropical cyclone, then you won't have any problem. So this is where we are. This is okay here, which means this is the region where we expect our tropical cyclone to take place. Okay, why? Because it's within the tropics. It's within the tropics. So the first thing that we talk here, saying there should be the presence of low pressure system, which means we need the convergence of air masses. Okay, remember it's within the tropics. There used to be convergence of air masses. As they converge, of course, they rise. When they rise, okay, let me get into that, okay? There should be convergence of air masses, that's number one. There should be presence of the Coriolis force. Coriolis force is responsible for deflecting the wind, okay? So in the northern hemisphere, winds are deflected to the right. In the southern hemisphere, they are deflected to the left, okay? So if you look at it now, you find that it's more effective from 5 degrees south, because at 0 degrees, there's no Coriolis effect. So it means it starts off at 5 degrees. So this is where it starts. Then it starts moving. It's driven by the easterlies, moving from east to west, moving towards this direction along the ocean. So we are saying now there should be presence of the Coriolis force. That's another condition that is favorable. Sea temperatures has to be 26.5 degrees and above. That is the other condition as well. The sea temperature is supposed to be 26.5 degrees and above. The calm conditions over the oceans, unstable conditions, and there should be also release of latent heat. Of course, it is the heat that is released when condensation takes place. That's your latent heat. There should be upper air divergence. Remember when they converge here, what happens? Okay, it rises before it reaches the tropopause, then it diverges. That's basically what you're talking about. So there is convergence, then there's divergence in the upper atmosphere. That's basically what you're talking about. So that's number one. You only write one thing. Give evidence from the map and table information that tropical cyclone Filipo is strengthened from 10 to 11. Okay. So you can see number one, it's exposed to more moisture because it's still within the ocean. Exposed to more moisture over the ocean from 10 to 11 March. Okay, 10 to 11 is still within the ocean. It's exposed to more moisture because this is what jet propel the process. It aids more moisture. Okay. Wind speed increased from 63 to 95. You can see it increased from 63 to 95. This is the evidence from the information that we have. 1.4.3, give 2 reasons for the decrease in wind speed. From 6 o'clock to 1800 hours on 12 March. So you can see why did the speed decrease. Of course, you should know what happens when it reaches the land. This is an indirect question that I ask you. As soon as it reaches land, what will happen? It moves over the land, which means there is less evaporation now because it derives its moisture from the ocean. So there is less moisture which means there's more friction, there's less latent, okay, it starts to dissipate. These are some of the reasons. Obviously, you should know what are the conditions on when it reaches land, what is likely to happen. There's more frictional drag that is taking place, it moves over the ocean, over the land, which means over the land, there's no evaporation that is taking place, which means the supply of moisture is now less. Because if it is warm and moist, that's when condensation takes place. That's when clouds form. That's when we have it has got more strength, it has got more power. But the moment it reaches land, which means there's more friction drag, less latent heat, it starts to dissipate. Okay. Then the next thing, number 1.4.4, it reads, on March 14, tropical cyclone Filipo reached the mature stage. Draw a labeled section of the tropical cyclone Filipo in its mature stage. Marks will be awarded in the following. So what we are doing now is, it's a matter of knowing the cross-section. What happens within the eye? What happens on the eye band? That's what you need to know. Okay, I'm just going to do a sketch here. Okay. I'm just going to do a sketch here. Okay. Then I'm going to label here as my eye. I'm going to do a sketch here. Okay. There is rising air. There is rising air. Okay. So here is within the eye. What is happening within the eye? Obviously, there's subsidence that is taking place, because we have got what we call too much subsidence that is taking place. Too much subsidence movement. Okay, sorry about my handwriting. Then here we have got cumulonimbus clouds. Cumulonimbus clouds, I'll just say CC, cumulonimbus clouds on both sides on the eyelids. Okay, so this is within the eye. We are saying that there's cold air as it is descending, of course. Okay, there's cold air that is descending. It's cold air is heavier, so it's descending. This will be your cross section. So obviously, when it's descending here, we have got more divergence that is taking, more convergence that is taking place. But as it goes up, there's more divergence. Of course, there's more divergence in the upper atmosphere. Then there's descending air, okay, which is within the eye. There's descending, there's cold, there's calm condition within the eye. But here you can see that's where the air is rising. As it rises, condensation takes place, clouds form, then we have got torrential rains. I'm talking about your cumulonimbus clouds. So air subsides here within the eye. Air heats up. When it heats up, what happens? It rises. When the air is up, it rises, moisture gets evaporated, air is dry, no condensation takes place here within the eye. That's basically what you need to show there. Sorry about my diagram, it's a little bit sketchy, but this is just to show you what you're supposed to show. Within the eye, there's calmness because there's cold descending air. Then on the eye walls, what is happening? There's rising, warm rising air, okay, that results in condensation, formation of clouds. That's basically what it's all about. Okay. Then from there, account for the lack of rainfall clouds in the eye of the tropical cyclone. Eye of the tropical cyclone. Of course, we are saying now in the eye of the tropical cyclone, air subsides. This is what is happening. Air is subsiding. The air heats up. Okay, when it's subsiding, what is happening? Okay, I'm talking about the dry adiabatic lapse rate now. What you call the dry adiabatic lapse rate is it is descending. There's an increase of temperature with a decrease in height. That's basically what you're talking about. So the air is heating up as it is descending. The same applies what happens with the berg winds. Okay, moisture gets evaporated and air is dry. That's basically what we are talking about. No condensation takes place. That's basically what we are talking about. So in the first one, on this question, we are supposed to call the cloud type. That is your cumulonimbus. I've said CC. Okay. The cloud type, I've talked about cumulonimbus. The eye, there's descendants, subsidence. Why? Cold air descending, calm, clear conditions. Air movement in the eye is going down. That's basically what it's all about. Okay. Then 1.5. which is going to be our last one, I think, in climate and weather on the 2024 paper. Refer to the source based on the line of thunderstorms. During summer, thunderstorms form a line that extends hundreds of kilometers. This line thunderstorm can persist many hours and produce damaging winds and hail, which impact negatively on the environment. Okay. So what I want to say now is, remember I was talking about the condition of what happens within winter and also summer. So remember I said that when you're looking at the summer now, what do we have? There is low pressure in the interior. Okay, let me go to the diagram so that I won't confuse you. Okay. So what happens now in summer is, okay, line of thunderstorms, okay, this is our moisture front. This is our moisture front. What do we have? We have got the South Atlantic high here. We have got South Atlantic high here. Then we have got the South Indian high here. Here there is cold and dry air. Here there's warm and moist air. Okay, cold and dry air, then it's warm and moist air. Here we have got a line of thunderstorm. You can see with these clouds that are formed here. So just to explain the diagram before we move on to answer the question, what you need to understand is within summer, we have got the low pressure in the interior just because of the intense heating that is taking place, number one. Number two, the changing of the intertropical convergence zone, which is our ITCZ, it has shifted, it has moved further south. So that's why we have got intense heating, that's why we have got low pressure in the interior. Okay, but our high pressure system, that is the South Atlantic high and South Indian high, they have both moved further south, you understand? So during this time now, because our Kalahari high is not active in the interior, there's low pressure, there's no high pressure, which means now the rising air or the wind that is blowing from these two high pressure systems, they can go above the escarpment. They can go above the escarpment or the invasion layer. This means that condensation can take place. This means that clouds can form. Okay, so we have got the cold and dry wind from the southwest, South Atlantic high. Then you've got the warm and moist air from the northeast, South Indian high. They meet in the interior, separated by a moisture front. Separated by a moisture front, which is a zone, a boundary or layer that separates two air masses with the different characteristics. An air mass is a large body of air with different characteristics in terms of its temperature, in terms of its moisture content. So these have got difference in terms of their moisture and temperature. Atlantic high is cold and dry. Indian high is warm and moist. So they've got different characteristics in terms of moisture content and temperature. Okay, warm moisture by its nature is light. So what happens with warm air? It rises. If it's carrying enough moisture with it, what happens? It cools, it condenses, clouds form, then we have got rainfall. Cold air by its nature is heavy. It does not hold any moisture. So it does not rise. What does it do? It sinks. Okay, so here we have got our South Atlantic high in an anti-clockwise direction, it moves towards the interior. We have got our warm and moist South Indian high, it moves in northeasterly direction towards the moisture front. So the moisture front separates the two. What will happen now is the cold and dry air from the South Atlantic high, it will undercut the warm moist air from the northeast South Indian, okay, high, causing it to rise. As it rises, cools, condensation takes place, clouds of vertical extent like cumulonimbus form, then we have torrential rainfall and line of thunderstorms on the eastern side of our moisture front. So you've got the moisture front, you've got the cumulonimbus. What else do we have? According to the extract, in which season do line of thunderstorms? Okay, obviously these line of thunderstorms, this is your summer. This is your summer. Describe the temperature and the moisture content of wind A and wind B led to the formation of line of thunderstorm 1.5.2. Obviously, this is cold and dry. A is cold and dry. It's coming from the South Atlantic high, which is a cold ocean. It's cold. Cold does not hold any moisture. That's why it is dry. Then your B is warm and moist. It's coming from the Indian Ocean, which is a warm ocean. That's why it's warm and moist. Okay. Then wind A is cold and dry. Then wind B is warm and moist. Then 1.5.3, explain why the heaviest rainfall case closest to the moisture front is evident on the source. 1.5.3, there's rapid upliftment of warm air along the moisture front, which means here they are separated by a moisture front. So there's rapid upliftment of this warm moist air from the South Indian high. Okay, that's number one. The warm rapid upliftment of air along the moisture front, which means here along the moisture is uplifted. Then it cools, the condensation clouds form, then we have got rainfall. There's greater condensation that takes place because there's vertical uplift of this warm west air from the South Indian high. Cumulus nimbus clouds form. There's less uplift of air from the moisture front, okay, obviously on this side, obviously because it's cold and dry. Okay, these are some of the things that happens. Rapid uplift of air along the moisture front, greater vertical condensation that takes place, then you've got cumulonimbus clouds form. Then 1.5.4, explain the negative physical environment impact of the thunderstorms. Of course, we are looking mainly on the natural environment. Natural habitats will be destroyed, ecosystems will be destroyed, Biodiversity will be reduced. Those are some of the things that you look at. Topsoil will be washed away, that is soil erosion. Mass movements can be triggered. Wildlife will be replaced or drowned. Trees, natural vegetation will be uprooted, destroyed. Water quality will be reduced. Increased leaching of soils, and so on and so on. So we are focusing mainly on the natural, that is the physical environment of line of thunderstorm. That's what we'll be looking at. So boys and girls, this takes us to the end of our November 2024 Geography Paper 1. Remember, I was focusing only on climate and weather. I want to emphasize something. Please, boys and girls, when it comes to climate and weather, the most important thing that we focus on is your elements of weather. This is where we want to see the implication. We want to see the effects. Okay, what do I mean by that? Think about one element of weather, that is precipitation. Precipitation, okay? That's number one. We want to find out, are we likely to have more rainfall or less rainfall? Precipitation, these are various forms of moisture that fall from the sky to the earth. So that's one thing that we are going to see. What is the implication in relation to the precipitation? Number two, we are concerned with the wind direction and speed. That's what we are concerned. Are we likely to have strong winds? Are we likely to, what is the likely direction of the wind movement? So that's what we also look at. Then number three, we are concerned with the cloud cover. Cloud cover, is it going to be overcast? Is it going to be partly cloud, or is it going to be clear? Then in number four, we are concerned with the temperature. Sorry about my handwriting. Is it going to be cold or hot? So whatever you're going to look at under climate and weather, this is where most of our analysis will be. Precipitation, what are the likely weather conditions? In terms of the direction of the wind, in terms of the wind speed, in terms of the cloud cover, in terms of the temperature, are we likely to have clouds? What conditions result in us having clouds, in us having heavy rainfall? So that's basically what we are talking about. So please, this is very easy. Take your time to understand the concept, but mostly at this level, it's more to do with application. Thank you so much.